Hello, my name is Zachary Davis. I am the coordinator of the Horizon 2020 project LEBED, which is looking at lightweight and flexible solutions for printed electronics. Today we're going to be talking about the pilot line infrastructure that is available through LEBED. But first we'll look a little bit about what is printed lightweight and embedded electronics. So the basic idea is that you are taking the classical PCB technology, which is a rigid FR4 substrate, where you're doing plating and lithography of copper in order to make electronics, and then of course mounting surface-mounted devices, and then basically using, instead of doing this, we go for printing processes to basically directly print layers on top of materials. In this case, you can imagine cheap plastic foils. In this case, this is basically the same thing, where it is an RF, sort of a temperature logging system with RF near-field communication capabilities, where you have the battery, you have the antenna, and you have also a small IC that's doing all the measurements and the calculations, but on a very cheap, thin, lightweight foil instead of a bulky FR foil composite. LEBED is set up in a way that we have the what it stands for is the Innovation Testbed for development and production of nanomaterials and processes for lightweight embedded electronics. You can visit our website and get started. So this is the single entry point. The single entry point is the LEBED website. Through the website, you can of course register, and we'll contact you within a few days. Once you're inside LEBED, there are three phases. First, we do go through a techno-economic modeling, which is basically assessing the getting information from the customer and trying to do some techno-economic modeling in order to understand what is can it be done, what are the economic, and a few other services. There's of course another talk about that, so you can go to there and then get more information about those services. But we're going to talk about today is the pilot project. So what happens there, we can actually get infrastructure access, and then after we do a pilot project, we go to a knowledge transfer, so helping the customer take the pilot project results and then go to market. If you want to understand more about, if just to familiarize yourself with the amount of customers, we actually have quite a lot of expertise within the project, especially in the pilot project phase. We have Danish Technological Institute, BS Particles, CPI, RISE. These are TNO, TENA, etc. These are very big infrastructure and have been in the print electronics sectors for many years and have a lot of expertise. Supporting that, of course, there's a lot of very nice SMEs and also sort of helping with the business side of things. How do we get this, these technologies into products? The pilot project, the types of pilot lines we have is threefold. We have three types of pilot projects. We have pilot lines, sorry. We have nanomaterial pilot lines, and that's for rapid development, but also production of materials. Then what we need to do, once we have a material, we need to formulate that into a printable ink. And then we have, of course, formulation development and production pilot lines for that. And then we have, of course, different types of inks. It could be an ink for printing. It could be adhesive for gluing components on. It could be lots of different things. It can also even be loading a sort of a functional composite. There's lots of different things here. And then of course we have our printing lines, and the printing lines is what's actually making the final sort of prototypes and components that go into, they can either be embedded in another application or be a product in itself. LEBED can perform proof of concept projects. That means I would say this is more very quickly sort of a very short project trying to figure out, okay, can an ID, is there a validity in a specific idea in a proof of concept work sort of, and then we can also then take that proof of concept and go to a prototyping phase where we make a sort of full system prototype of something that's working with electronics, new materials, even some sort of readout electronics, wirelessly, data transfer, etc. And we can then take those components, those prototypes, and then go to a pilot production. If we go to the specific sort of material, and if we talk the nanomaterials, we actually have quite a few. First of all is the supercritical flow pilot reactors, and this is at the Danish Technological Institute, and this is just some images of the pilot lines we have there. And this is for making these are sort of flow chemical reactors that use supercritical fluids such as water or ethanol or other solvents to make very well-defined and small nanoparticles, basically. We have also built solvothermal batch pilot lines, and the main difference here is instead of a flow synthesis, we have a batch synthesis where we basically just collect liquid in a big vessel. We do it in the correct first we have the one reagent and the second reagent, we can pump them in automatically. We have a sort of a semi-automatic pilot lines that can do that can actually inject different chemicals at different times, heat it up, cool it down, etc. We can go up to 80-liter jacketed reactor. We can also use these systems for rapid screening, but we can also use them to produce kilos of nanomaterials per day. Most of the systems here, especially the ones you see in the image, is actually PLC automated and has also inline process monitoring. Just to show you some of the developed nanomaterials for the electronics, some things we're looking at. For example, silver nanoparticles, and this is obviously silver is a sort of a the main material used for printed electronics today. Most of membrane switches and that kind of products that are on the market are using silver as their conductive material. So we're also using silver nanoparticles in that case, so trying to make that for inkjet and valjet and lift print technologies. We have also developed silver nanowires, and the silver nanowires are very important for transparent conductive layers, as I'll show you some examples in a minute. And then we also have developed another material called copper. Maybe you heard of that, but copper nanoparticles for inkjet and screen print printing print lines. And the idea of copper is to make a sort of a cheap, sustainable alternative to silver. Bulk silver is usually about a few hundred times more expensive than copper. So that is actually a huge push to try to go into more sustainable, more cost-effective materials, and copper could be one of those. And we are developing that, and I'll show you some examples of copper-based inks. Finally, we have also done some dielectric like barium taugenate, but we have done a few different types of sort of non-conductive dielectric, but also sensing materials as well. But we can do quite a lot more. This is just a small example of what can be done. We also have a gas phase pilot line through the partner VS Particles, and this is an extremely cool sort of pilot line that can actually take bulk materials, metals, even oxides, and then sort of atomize it into tiny small particles, and then basically directly write them onto a surface. This is a demonstration of the process. So this is actually direct writing some silver or other conductive material on the glass, in this case just the glass, and then you can see they're just writing some lines. It's quite fast and quite reproducible. And this is really good for if you need to small area printing where it's actually in a case where you need a very specific sort of rare material that could be for example a sensing material or some other types of exotic material that you can't do using large scale printing, for example. If we go into the sort of formulation pipelines, one of the things we have been very good at is actually in the rapid screening. So one of the really main pain points for development projects using these type of things is, I mean, usually if you have to develop a material and then an ink for a specific process that goes into it, that is something that could take years of work, and it typically takes years of work to go from an idea to a material to something that's inside a product. One of the things we really want to do is to sort of decrease the development time to below maybe 3 to 6 months. And one of the ways we do that is using AI and robotics. So the idea is that we actually produced copper particles. That was actually DTI that did that. And then we basically, CPI was able to, using a robotic system and an AI sort of development scheme, to sort of, what do you call it? Find the compatibility of the particles with different solvents. So what you see on the right-hand side is the sedimentation time when we put the copper into 37 different solvents and trying to understand which solvents is compatible with the particles. And as you can see, some of them are very good and some of them are extremely bad. And it's something you don't really know. And then once you have that sort of solvent particle compatibility map, you can then use that to make the ink. And so we're using this sort of AI or design of experiments, measuring on different solvents, mixing the solvents, and then measuring the particle dispersion, and then using that in order to make the inks. And what we were able to do in this case was to make screen printable formulations that containing copper nanoparticles around 20 to 30 weight percent, which is a DGME based solvent, and we were able to make a nice inkjettable ink using the silver, and actually also then with the pilot lines, the DTI, the printing pilot lines, the digital printed pilot lines, produce several components like this NFC antenna using copper instead of silver on paper. RISE has also been looking into formulations of other more cost-effective materials using zinc-based inkjet formulations. So in this case, they have quite a good sort of conductivity using extremely cheap zinc nanoparticles. And they're also, instead of using a thermal or photonic sintering, they're using a chemical sintering process. So the idea is that you print first with your zinc, and then you print on top of that a chemical curing agent, which then cures the zinc, and they are actually getting quite good results in that. So zinc is another alternative to silver for a cost-effective, high conductive material. If we look at the component pilot lines that we have at our disposal, it's actually one of the bigger sort of packages we have. And we can sort of categorize the component pilot lines into two types: the prototyping, so the systems that are used for producing small amounts, but have a very fast turnaround time, where we can print, test, print, test, print, test. And then once we have that, we can actually go into more of a production setting where we can use more sort of sheet to sheet, but also roll to roll systems to produce large amounts of one type of component. We have in the prototyping, we have basically two types of digital printing system. We actually have a 3D multi-material system, which has been developed by TNO with the help of TU Eindhoven. And we also have sheet-to-sheet inkjet printing through Danish Technological Institute and RISE in Norrköping. These are very good systems for printing small amounts to sort of test designs, reiterate designs, etc. With the 3D, this is actually even enhanced, so you can really go from a thin film, sort of a foil, to something a really 3D printed structure. And the production lines we have, of course, roll to roll. We have screen printing, flexogravure printing. We also have CPI has a IoT sort of a roll to roll component pilot line where they can actually put components onto a foil that's on roll to roll. And RISE is actually developing a large format inkjet printing, so sort of a roll to roll inkjet printer which can go into a large volume production. Just to give you some examples of these components, there's quite a few of them. I would say IoT components. This is an NFC antenna. Capacitive structures are very good for gas or touch sensing, mechanical strain sensing, LED lighting. There's actually quite a lot of application areas for these type of components. Just to give you also a good example of what 3D printing is good at. This is a fully embedded temperature logging system where we actually printing the whole sort of the substrate using a 3D printing processes, then actually filling, and then what you see, the printing the cavities, we then place the components in there, and then we print the grooves, and then we fill the grooves with the conductive material, and then we fully embed it, encapsulate. So the whole thing is actually encapsulated in the polymer. and this is a sort of a validation of the 3D printing capabilities of TNO and Hull Center. This is an example of a sort of I would say, a collaboration where we were trying to make capacitive touch and LED lighting on the same foil, and this is actually done on a PET foil, a plastic foil, 4 layers printed on the same side of the substrate, silver dielectric, using a sheet-to-sheet flatbed screen print process, or we have also used a digital inkjet process for the sort of prototyping phase, and then made the pilot production using a screen print printing phase. Finally, we have also developed sort of a nice thing is to show you how we sort of combine the different phases. So in this case, we actually developed the silver nanowires, and then took those silver nanowires and made into a printable ink, where we actually had quite a lot of challenges in that, making the ink so you have a very nice thin, smooth surface to get the optical properties just right. And then we actually made use the nanowires to make a full prototype of sort of a transparent interactive display. So this is as you can see, the first where we have the electronics on this transparent foil, and then we have touch interaction where we're touching, and LED lighting on the same foil, and it's basically seamless. You cannot see the electronic. You just see the foil, but you don't see the actual wiring because it's based on this transparent conductive material. And then the last sort of example is the Axiona, and the Axiona is actually trying to embed sort of structures into composites. So taking the foils, we made prototypes and also some pilot produced NFC sensors with NFC capabilities, and then embed them into a protrusion process, which was done by Axiona. And then we have also this embedded touch and LED lighting into an inkjet molded foil. So this is also produced and developed foil, which has the LED lighting, touch, and also electronics inside. And then how we actually had to a lot of development on the materials in order to survive putting them into an injection molded mold, which is high temperature, high pressure. So this is a very interesting but also very challenging project in terms of trying to get especially the LEDs to stay mounted on the foil during the injection molding process. So this is something that we have a lot of experiences now as well. Finally, I'm going to talk a little bit about the characterization services, because of course you cannot do any of these things without characterizing both the materials, the inks, and the components when you're done. So just to give you, I mean, we can of course do all this. We have this in-house in many of the partners, but some things of one of the other things we've been working on is inline characterization as well. CList has been working on this, so they have done a lot of radiographic quality control. So they actually have a system that can then take X-ray images of the printed layers and then compare that to the sort of design. And when you do an X-ray imaging, it's actually quite, so as you see here, this is a photo of optical photo where you can see a sort of a scratch, two types of scratches. And when the one, actually, if you look in the X-ray image, it doesn't seem like a scratch at all. You're just scratching the surface, but not actually penetrating the whole metal layer. Whereas in the other scratch, you can see that you have disconnected, the wires are disconnected because the X-ray image is giving a much better contrast on where there's metal and where there's not metal. So this is an extremely useful quality control tool. We also have Fraunhofer working on the characterization, and one of the more interesting techniques they are using is micro and nano CT for quality control. And this is basically, so micro and nano CT can basically generate a 3D image of an electronic component. So as you can see here, you can see that there's you have wiring, wire bonds, so you have the PCB, you have a chip, etc. So this gives you really nice sort of idea of, okay, is there something wrong but you can't take it apart, then you can use these non-destructive technologies to really understand where the quality and where things have gone wrong in your electronic components. So this is just some of the very nice quality control, the characterization facilities we have at our disposal. With that, I'm going to say thank you very much for listening. And if you have, of course, any more questions or you want to know more about our pipeline facilities, please contact Libed, and we'll, of course, give you all the information you need. I would, of course, push you to visit the Libed single entry point website and get started today. So with that, thank you very much. And yeah, hope to see you soon.